Hi everyone. In this video, I want to talk a little bit about data portraits and the animation that you see here. This interactive portrait is a kind of parameterized set of images, layered images, and they're responding to my movements, to my face, by means of the webcam and some machine learning tools. This particular set of parameters is inspired somewhat by the work of Accurate, and in particular, Giorgia Lupi, who is the co-founder of Accurate, and also a TED speaker. Here we see some more examples of these data portraits, and Giorgia took it on themselves to create a taxonomy. And so the taxonomy is described here. Each of the answers to these survey questions correlates to a particular kind of visual expression. So Giorgia has brought her design chops to bear on perhaps a mundane process of gathering data and sort of brought it to life. This is the inspiration here, and I've also made my own version based on my responses to Giorgia's survey. And these responses take the form of layers in a Photoshop file here. But as we saw, they also come to life when I animate them in this P5js sketch that is also powered by machine learning. So in this video, we're going to take a look at the code behind this 2D mirror data portrait to see how it's put together and maybe adapt it a little bit further for our own purposes. You can find the code for this on my GitHub here. The URL will be in the description. You can see that in this GitHub repository, I've got all of these PNG files. Those are the layers from my Photoshop document, my own iteration of George's survey. Here they are on my local drive as well, these different layers. So by exporting your Photoshop layers to PNG files, you make them available for the web. And so, just as a hint, if you're in Photoshop, there's a way to do that here. Export layers to files. That's a nice way to go about that. That's how I made these PNG files. Also in my GitHub repository here, you'll see there's an index file, a sketch.js, and another file called Replit. Replit is also useful to us as a way of deploying something from GitHub, or in fact, testing out and coding in real time on the web. And I've used Replit to, in fact, host this project as well. On Replit, you can import from GitHub your repositories and have them launch. And that's what I've done here. I'm not going to focus on Replit here, but just to give you some context, it's a great way to put your code up online, collaborate on it, and also launch it. And so here I am in the 2D mirror sketch as I have it on Replit. And so again, we see the same set of PNG files. We see an index.html. Let's take a look inside here. Notice right now it says, for the best experience, open a new tab. That's the new tab I have here. I've set this up because really putting the webcam view inside of this window isn't a great experience. And Replit doesn't like it very much because I have all of these webcam libraries, machine learning libraries that I'm using. So you'll see here in my sketch that I'm importing TensorFlow and BlazeFace. These are a couple of machine learning tools that are able to do facial tracking, recognize some of the key points on a webcam feed, points like the eyes, the ears, the mouth, and so on. And we're using in this sketch those key points to track where is the user in relation to the webcam, and then in fact building from that a kind of user interface. So I'm not doing any clicking here. This is hands-free UI. I'm using only my head to control this sketch, which is kind of nice. That's only possible because TensorFlow and BlazeFace are doing this analysis in the background of that video feed, identifying the key points. So I also include here P5js. Let's make this a little bigger, which of course is the JavaScript child of the processing environment, making coding accessible to artists. So here we are using P5js as well. P5 helps us to put the pieces together. It's not enough to use machine learning to track where the face is. We also want to do something with those data points. In particular, we want to use those data points to control some images and some layers, which you may already know how to do, make rendering images in P5, but now controlling them with our heads. So here are the images. Here is my kind of index file that includes the libraries that I need. And this is the tab notice. It's sort of there to prevent things from getting messed up inside of Replit. You could probably remove it and it would be fine. So the key thing we want to look at, of course, is sketch.js. That's where the action is. Let's go there now. I've got a bunch of notes here in my sketch.js describing what the sketch is about. So you'll see that it's about tracking the user's face via webcam. It's about using the head movements as a kind of control mechanism. It's using facial orientation, and it's calculating from that the proximity of the face. Are we further away or closer up? As we saw, we can scale up and down these images just by moving forward and backward in relation to the camera. And those layered images are reacting dynamically to head movements. Okay, and then there's the BlazeFace model. That's a machine learning model, which has been pre-trained to recognize faces. And you can read more about BlazeFace here. There's a BlazeFace card, model card that Google has created. Google also are using the BlazeFace model as part of their MediaPipe toolkit. And in this PDF, you've got a whole set of details about this model. How you can cite the model. So Bazarevsky et al. Are the originators of this model. And it was published first in 2019. There are documentation links. This is the paper that it is linked to. We can find out all about this model. How does this model function? How well does it function in different areas and different environments? What are the parameters? Notice something here about roll angle. Maybe it has trouble recognizing my face beyond 45 degrees, for example, right? The rotation has some limits. It has some metrics here. This is really interesting and useful as a way of qualifying what kind of a model is this, and are we really happy with it? Also from, let's say, a social perspective. Fairness evaluation and so on. Are we representing everyone fairly in the model? And so we can benefit from these model cards that Google have produced. And here I'm using the BlazeFace model and just referring to it in the sketch. We saw already the work by Georgia Lupi and Accurate as the inspiration here. And you might take this further. So some questions to consider. How does data visualization relate to artistic expression? These are just some questions that I'm also asking in this work. How might a data portrait differ from an infographic, right? There's something about George's work also that reminds me of an infographic. This is that. It's a bit like a data chart. But it's also somewhat expressive, and it has its own visual vocabulary that's more dynamic than that. How and why is data presented and represented? Is it shown as qualitative or quantitative or a mix of both? How might you adapt this for your own data portrait? So some framing there that might be helpful. And then we get into the sketch itself. How does this work? Well, there are some things we have to keep track of. I'm using, as we saw, the model. I'm using the webcam. There's a canvas that is being painted onto. So these images are being painted onto a HTML5 canvas. And P5js is helping us with that. We might need to keep track of faces that the webcam sees, or rather that BlazeFace is seeing, but BlazeFace is detecting or predicting. Yes, there is a face that I see in this webcam feed. So we need a place to put them. This is an array because there might be more than one, and really in this version of the sketch I'm only using the first face that it finds, but there might be multiple predictions that it makes. If there are two faces, that array would contain more than one. We'll also have images. So we have 7 of them in this example, and they need somewhere to live, so I've created an image variable for that. There are landmarks that the BlazeFace library is going to locate for us. Eyes and nose and so on. I'm only using a couple of them, the eyes and the nose in particular, but there are other ones too that you can draw from in the BlazeFace model, and that's documented elsewhere. But I've created here a structure that will hold the X and Y position of each of these features of my face. And once you know those things, you can then calculate the angle, the scale, and the center. So let's say if I tilt my head this way, what angle is that? And you can calculate that angle based on where the eyes are in relationship to each other. You can also calculate the scale, if you will. If I move closer to the camera, the distance between the eyes increases relative to the webcam. As I move further away, the distance decreases, so I can use that to calculate, if you will, the scale of the face. And in turn, the scale also of these images that I seek to control, input and output. Scale here is both a kind of input of the face and the output on the images. There's also a scale there. We're mapping the one really onto the other, as we'll see. faceCentre also is a point around which point should we rotate these elements. And really, I'm just going to use the nose as my reference point for the center of the face. Okay, so those are the things we want to keep track of. They each got a variable. Here we have now a preload. This happens before anything else. And P5, in order to render these images, needs to have them loaded in advance. So here I'm putting those images into an array and just loading them all up. I've noted here that the order is important because the stacking somewhat matters. And so here you have this kind of yellow block and the gray block. They happen to be called rules, and workspace have put them first in the array. That means they're on the bottom of the stack. And so they will render first. We don't want them to conceal the other layers that are more delicate and intricate. And so the stacking here is important. You could rearrange this and see that things are perhaps a little different. If I take this one, put it at the end, we will have again a different layout. So if I rerun this, let's see what that looks like. If I launch this now, I've just reordered the stack of those layers. And now that gray block is on top, kind of concealing everything. Probably not what I wanted, but the point is clear that the order of things is important. So I'm going to undo that and rerun. So I have back the original back in view. And so having done that, nice thing about Replit is you can launch that immediately. That's pretty cool. Save and launch. Very nice. So after we've loaded our images is the setup. This is the next thing that runs in P5. And the first thing we see is that it's checking, are we inside of an iframe or not? And so if you're in an iframe like this one, it doesn't work very well. And so basically this is little tab notice, as it's called, tab notice, is being displayed. We saw that on the index here. Tab notice. That's all of this stuff with the green button. And so yeah, so if you're inside of an iframe, it just shows this launch button and that notice. And we don't proceed beyond that in that case. Replit doesn't do a very nice job in there of dealing with all of these libraries. So we put it full screen and it works fine here. So what if we are in a full screen mode? Then we make a canvas. That's the next thing we do. And notice it's a WebGL canvas. That helps with faster rendering. It uses the graphics processor then to display those images and lay out the canvas. There are some quirks that you should be aware of when you create a canvas in P5. The WebGL mode is not the default. But when you're in WebGL mode, the origin of the canvas is actually in the middle of the screen, whereas normally it would be in the top left of the screen. That's something to keep in mind. It comes up later when we think about where we position things on the screen relative to what origin point. Okay, then we capture the webcam. So P5 has this create capture. Basically what this does is it puts a video element into your page and it attaches the webcam to it. Notice I've said here initialize as well. And that's initialize here is the name of a function. It's down here on line 90, initialize. This is the function that will be triggered after the capture has been successfully started, right? The webcam will not launch immediately. It will take some time to start up. And so only after the webcam is ready, then we can proceed. And the way we proceed is by means of this initialize. You could call it whatever you like. Any function name, let's say, you could put in there. But initialize is what I've chosen to call it because that's what it is. The webcam itself is actually hidden. In this data portrait, you don't see me in the web browser. You see me here in the bottom corner, but not inside of the web page. The web page doesn't bother trying to render the webcam itself. Instead, it's rendering this kind of data portrait, an abstract representation, if you will, of me through my data. And so the webcam itself is hidden. You could comment that out and we would see the webcam as well if you'd like. Try that. Now I have a little frames per second counter. You see that on the top left. It's not performing great right now because I'm also at the same time recording my screen. So normally this is up around 30 or 40 frames per second. This is just creating a little div there at the top, putting an ID and a position on it. And what you see further down is that this frames per second number gets calculated and popped into that div. That's it for the setup. Beyond the setup, of course, is the initialize. And so once the webcam is ready, that's a kind of a loop that would start or a function that would run. So that's the initialize down here. We will look at that in a minute. But first, let's look at this draw function, which is triggered automatically by P5 to be running at 60 frames per second. So this is going to loop 60 times a second. P5 is going to run this. And so what will it do? 60 times a second, if it can. It will fetch landmarks from my face. It will get the angle and the scale and the center. Just try to figure out where I am. And then only after it has done that will it proceed to draw the images. So that's the overall logic of the sketch. We have landmarks that are fetched from the face, angles and scale that are calculated, and then images that are drawn. That's the overall logic. Notice these are different functions that are referred to in this draw loop. So it might seem like this draw loop is pretty short, but actually each of these steps is dealt with in their own right. Further down, these functions are defined, so there's a whole bit of math to do for getting the angle. There's a whole bit of getting landmarks, that is the BlazeFace, the machine learning part. That's done further down. And notice we only do that if there are in fact faces. So faces.length greater than 0 means we've actually detected a face. If there is no face that is detected, then you'll see that it disappears. So let's try that out. If I was to do this, if I block the camera, the images also disappear, don't they? And so if BlazeFace doesn't detect my face, it also will not draw any images. That's the interesting logic here. If there are 0 faces, nothing happens, right? But if there are faces, we're going to take the 0th one, or the first face, and work with that. So you could, of course, loop through all of the faces and build that, but I've kept it simple in this case. So remember that initialize that we saw earlier? This is running in some ways parallel to the draw loop. It's triggered immediately from the setup here. After the webcam is finished loading, we initialize. And that's triggering the launching of the BlazeFace model, right? Which is a TensorFlow model. TensorFlow being, of course, a machine learning toolkit that you can use in JavaScript. Here we're using something called WebAssembly. So the BlazeFace model, it can run in different ways. It could run on the CPU, it could run with WebGL, it could run with WebAssembly. These are different ways of leveraging the hardware on your computer in the browser. And WebAssembly turns out to be very performant for this model. And so I've set the backend to be WebAssembly. You can see I've also included in the index, there's a reference to that here. WebAssembly, WASM, WebAssembly. That's that source code that is needed is included here, and you can read up on that elsewhere if you'd like. For our purposes, just know that this is helping with performance, making sure that BlazeFace is performing blazing fast. And then what we do is we load up the model. This takes a little bit of time. So you see here this keyword await. It's modern JavaScript. See also here async. So things might be running asynchronously in JavaScript. And that's interesting because if something needs to happen first, second, third in sequence, we have the ability here to control the flow of that logic. We cannot, in fact, find faces until we have first loaded BlazeFace. And so that's why it says here, await. That model is not going to be instantly available, and so we are controlling here the flow of that. If you're curious about async and await, you can read up on it on an MDN, Mozilla Developer Network, has a nice page about that async function. It's promise-based behavior, right? And so it's a nice kind of elegant, clean style. It's a way of dealing with the flow of what happens first, second, and third. So BlazeFace has this kind of loading function built in, and that's what we're calling on here. After it's done, we're going to run another function called find faces, right? So this is a little initialize loop. It's like taking TensorFlow and BlazeFace and loading them up. And once they're ready, once they're loaded, then we can proceed on to the next step. So find faces is just right here. It has its own function. And this is a kind of a loop that BlazeFace is doing independently of P5. P5 has the draw loop, 60 times a second it's going to run. BlazeFace also runs a loop here, and it might run slower than 60 frames a second. It's fast, but it's not that fast, let's say. So the machine learning toolkit, depending a little bit on the performance of your computer, is also going to have a variable frame rate. That's the one I'm showing here. So it's hopefully around 30 if everything goes well. And we're tracking that. So do you see how it says performance.now? I'm using a little timer. Performance.now gives you kind of how many milliseconds have elapsed. So that's another thing you can check on MDN. A high resolution timestamp measured in milliseconds. So what I'm doing is I'm recording how many milliseconds does it take for BlazeFace to detect a face in the webcam feed. And there's the start time and the end time, and in between it's going to estimate faces from the webcam, right? And so here we're just measuring, we're not only estimating faces, but we're measuring how long it takes to do so. And then we're updating the frames per second counter. And so that's the little div that we created up here. Frames per second counter. P5 lets you create a div, right? And put it in a variable. So that's the little thing at the top left here. And P5 is, because it's in a variable, we can come back to it down here and say, okay, put some HTML inside of that div. And in this case, put the frames per second here that we've calculated. And it's essentially the end minus the start. That gives you the time elapsed in milliseconds. And so to put that in frames per second, we do a little bit of math here. We also don't show it on every frame because then it's hard to track. So I show it on every 5th frame. And when that's done, when we're done estimating faces, then reporting the frames per second, then we do it again. So after we're done finding faces, we do, again, find faces. So this is showing you how it's a kind of a loop. It runs continuously. And that request animation frame is sort of like saying, when this frame is done rendering, run this function. All right, and so this, much like the draw loop, is just going to keep going and going and going. It's, in one sense, it's calling itself, right? And it does so at a slower rate. So this is the prediction of faces per second. You might notice that the animation itself is still pretty smooth. So P5 continues to run at 60 frames per second or whatever it's capable of. This is simply the frames per second for the prediction of faces. It's almost like we have 2 frame rates there to track. And so what is P5 going to do now with all of that? So if this is successful, if the model is able to locate faces, it's going to put them in here, right? Faces equals. And that's a variable that we've seen, and it's globally defined. So the draw loop will also have access to it. And in fact, we've seen it before. That faces variable is also in our draw loop. It's up here in our draw loop. If faces.length is greater than 0, so if the BlazeFace is indeed finding faces, the draw loop is going to say, ah, yes, I should go and draw some images because I have faces with which to correlate them. And so you see how that happens simultaneously. So what else do we have here? There are some more functions below that are more focused on dealing with the data, right? So here's one, it's called get landmarks, right? And we can see that we already had a structure for that we defined at the top here. This is what a face looks like. A face has a right eye, a left eye, and a nose. And each of those in turn has an X and Y position within the grid of the webcam. So by default, they're just set to X equals 1 and Y equals 1, but those are not useful values, right? So now that we've detected a face, we're going to populate this structure with actual data. And that's what happens here in the get landmarks. So given some data from BlazeFace, we're going to pull out just the relevant pieces of that data and format it in this structure that gives it a name and an X and a Y value, right? So that makes it easier and more human readable, that this structure makes our code more legible in a way that we can define things in terms of their actual names. I'll note here as well that I'm using something called LERP. This means linear interpolation, and so this helps to smooth out the data. Okay, so in fact, you could avoid using LERP altogether and just do something like this. It would in a way be simpler. We could just get the data directly from the BlazeFace landmarks that it detects. And here I'm saying 0, 0 because that's the 0th landmark and the 0th coordinate. That's a bit difficult to read, and maybe that's also why we're saying here we're defining this structure of right eye X and Y, left eye X and Y. It's more human readable. Well, suffice to say, this is where we're pulling our data from, but we're also LERPing it, meaning we're averaging it with the previous value. So wherever the right eye was before, now we have the new location of the right eye, and we're averaging them sort of in the middle. What is the midpoint of each of those things? And so we're doing that actually for each of these points, as we're finding the midpoint. That has the effect of smoothing out the animation. And I do the same thing here with get angle is being LERPed as well. So that LERP comes back. All right, so how do we get the angle? We've got the right eye and the left eye from the landmarks data. Now, as we see in the draw loop, after we've got those landmarks, we've defined them as a data structure. We can pass that along to get the angle, the scale, and the center. It's not enough to know where the eyes are. What, in fact, is the angle and the scale? We have to derive those things. So first, get angle, we pass along the face data structure. Okay. So to get the angle, we pass along the face. And there's a difference between the left eye and the right eye. So we say the dx, meaning the distance along the x-axis from right eye to the left eye. So I'm taking the right eye x and subtracting the left eye x. That's this distance in terms of the x value. We do the same thing vertically for the y value, subtracting them. So that breaks it down into the x and y components. If we were to express that as a slope, it would be like the rise and the run. Yeah, slope equals rise of a run. Now, but that doesn't yet get us an angle. So for the angle, we need to use tan inverse. So if you have the inverse tangent, if you want to read about the math, there's a nice little diagram here on MDN about it too. I think they have, so the a tan 2, it's a bit like the general scenario of what we want. Imagine this red dot is my eye and the origin is the other eye. This is the angle that we're looking for. That's the rotation of the face, right? How rotated is the face? And so we use atan to do that, and we also have to handle positive and negative values. Because if my head is centered, and then I go this way, that there may be a positivity or a negativity, and so the resulting angle we have to deal with whether it's positive or not. There's a kind of a change in sign that happens. So you can study the math for that if you want, but in the end we basically have a new angle. Let's say this is the new angle for where the face is that we've calculated here using the inverse tangent. So if you know where the eyes are, you also know the angle of the face now. And again, I'm LERPing it, meaning whatever the angle was before, calculate the new angle, and what we're going to return is the midpoint, somewhere in the middle. So it will gradually tend towards the new location of the face, rather than kind of jaggedly popping to that new location. So LERP has the effect of smoothing out motion. Similarly for scale, we pass along the data, the face data, and now it's more about the gap, the distance between these two eyes. And P5 has a distance function built in. P5js has a distance function. We just pass along the location of the left eye and the right eye, and it figures out the gap, the space between, right? So maybe it's 300 pixels in terms of a webcam, or maybe it's a lot less than that. If I'm further away, it'll be smaller. Maybe it's 100 or 50. And so that's an interesting number, but we want to have maybe a number that's more useful than that. So instead of having a range from 0 to 300, I might want to have a range from 0 to 2. And so here we're mapping the gap onto a more useful number. A number like 300 pixels isn't that useful in terms of rendering our data portrait. 300 pixels, okay, that's only in terms of the webcam, but I might have a screen. The screen size might be a lot larger than that. Maybe my webcam is only 720p, but my monitor might well be 4K. It operates at a different scale, right? And so the helpful thing here is we can generalize this, normalize the scale into a useful range. And so that we're saying, let's give it a number between 0 and 2. So a number between 0 and 1 will imply scaling down. A number between 1 and 2 will imply scaling up. And so that's how this is happening, right? So a number between 0 and 2 is more useful than a number between 0 and 300. Again, we're lerping that to get smooth motion. And finally, the center of the face is really relative to the nose. So where is the nose? And where is the nose relative to the webcam? That's what we want, really. It's like a fraction. Again, normalizing it, it's now going to be a value between 1 and 0, right? So it's not just I need to know where the nose is. I need to know how far is the nose from the left of the canvas, and let's express that as a fraction, as a kind of percentage. And so that's what's happening here. The nose x divided by the webcam width expresses the location of the nose as a number between 0 and 1, much more useful as something we can generalize. Because now the images will render also in a corresponding way relative to the edge of the monitor, relative to the browser. That same percentage distance, the images will now display there. So finally, we have the drawImages function here. And this is all about placing those images in the right spot. And so you see that there's a translate, there's a scale, and there's a rotate happening. And then finally, the image is being rendered, right? And so what the unique thing here that I've added is I've also added in something called liveliness. And so as we see, there is not all the images rotate at the same rate. So as I move around, for example, that gray and the yellow do not stay aligned. They kind of change in relation to each other, right? It's like the gray piece rotates more prominently than the yellow one. And that's what I've called liveliness here. And it's a function of the index. So here we go through the array of images, and each image has an index, right? So let's go back there for a second. Here's my array of images that we preloaded at the top, and we could number them. So 0, 1, 2, 3, 4, 5, 6. That's the index, is that number. The 0th image, rules.png, has index 0, and the first then image, workspace.png, has index 1. We can use those numbers in a kind of interesting way, and so the further I go through my index, the more lively my image becomes. So here I'm taking the index number, multiplying by this value, and setting a kind of liveliness. So that liveliness is going to now attenuate or modify or enhance the face angle. Not only am I rotating the face or the images based on the angle that I've found, I'm also adding this kind of extra factor to it, the liveliness factor. They've kind of made it up. I don't know what liveliness is. You could also make up your own factors here. You could make up your own tweaks to how these images are displayed, perhaps based on other parameters. Here we see that I'm resetting the canvas origin to the top left, and I mentioned that about WebGL, that it centers the origin in the middle of the canvas rather than the usual P5 method, which is top left. So that's just a kind of a reset here. Once we've reset, we take the center of the face, we multiply it by the actual width of the screen. It's different from the width of the webcam, right? And so you see here how it was useful when we did get center. We did that as a fraction. This is now a useful number, a normalized between 1 and 0. We can simply multiply that by the width of the screen, and then it's going to position those images relative to the full screen. So I get really the full width of the screen is represented here. Even though the screen is much wider than the webcam, it works just fine. Finally, there's a little window resize function here. If I resize the canvas, it'll still respect the canvas size. And that takes us through the sketch here. I encourage you to explore, play with this, and maybe you'd like to add your own images and logic to it. I hope it's been useful and enjoy.